This is no ordinary robot. It has been specially designed to refurbish the inside of this unique cavity. It works with human control to install special heat-resistant tiles and handle modifications to the structure. Sophisticated computer programs guide the robot towards any destination on the surface. This cavity will hold hot gases at over 100 million degrees centigrade as part of one of the most ambitious research projects ever mounted. Just 15 kilometres from Oxford, Europe has come together to try to harness one of the most basic forms of energy, the energy which drives the sun itself, nuclear fusion. The project is called JET, and the JET experiment is now entering a new and exciting phase.
10, 9, 8.
For scientists, the dream of an essentially unlimited supply of energy is providing one of the great challenges as we enter the new millennium. For beneath the veil of high technology lies an almost inexhaustible energy source with built-in environmental and safety advantages. What underlies the dream is that the fuel which powers such fusion reactions derives from the elements found in water. It is the fusing together of the isotopes of hydrogen, deuterium and tritium, which releases the energy of the fusion process. Standing in the path of this glittering prize are problems of technology and science, which will draw on the ingenuity of individuals and organisations alike in the decades ahead.
One of the dome cameras and one of the mobile cameras.
Yeah. So what we might have to do is, if we want to assemble the whole system up in the training...
These new pioneers at JET must conjure success from the use of new materials at the limits of their capabilities and the most sophisticated control systems to run every facet of the experiment. Scientists and engineers from across Europe work closely together to tackle the problems which must be solved if fusion is to become an economic source of energy. One group is using the latest laser technology to look inside the fusion chamber and measure conditions such as the temperature. The laser beams down from a roof laboratory. The alignment of laser pulses is one of many checks before the real experiment gets underway. The particle which will indicate the success of the fusion reactions is a neutron, and special detectors to count these atomic particles have been designed by another international team working at JET.
Yes, I can tell you there could be a number of reasons why.
Other teams measure emissions such as X-rays, which help to pin down the position and density of the fusion plasma. All the vast amounts of data are sorted, stored and analysed by computer specialists. The JET experiment is highly sophisticated and an adventure as exciting and focused as a space mission. The whole apparatus is now modelled in virtual reality, run from computers on the JET site. The complex jigsaw of magnets, detectors and other components can all be manipulated in virtual reality before the real designs are implemented. What lies at the heart of the JET experiment is the aim of producing a stable plasma, which is a very hot gas of particles as exists in the sun and stars. This will be used to generate energy. One approach that has gone a long way to proving itself is to constrain the plasma in a torus or donut-shaped configuration. The plasma is held in place by powerful magnets. The problem is that it takes very little to destabilize the plasma. The heat and particles which emerge from the plasma need to be used or managed. In this latest phase of JET, a new device is being installed at the base of the torus cavity. It's a carefully shaped channel surfaced with special tiles, which JET scientists and engineers believe will trap exhaust products and greatly improve the performance of the machine. The JET experiment is part of a long-term effort by Europe to harness its collective talent in fusion research. For inhabitants of the Earth in 50 years' time, interest in fusion today may be no idle curiosity. For choices may have to be made on energy sources by the next generation of crucial importance to the planet.
Can you see the transformer limbs and the orange steel around? You can see part of it.
start producing useful fusion, the scientists of tomorrow will need to reach an important milestone in managing a plasma. Containing a plasma is not enough. The temperature has to be high enough. It must be dense enough. And the energy be kept in the plasma for long enough. This hat trick is called the triple product. The target is to do this fusion hat trick well enough so that the fusion reactions become self-sustaining. This key condition is called ignition and remains the long-term aim for fusion experiments.
USA, Japan, from the Russian Federation and from the European Union.
A central goal for JET now is to help define the physics for the next generation of experiment, expected to be a world machine called ITER.
What we foresee is a series of experiments running from 1983 when we started up to 1999, looking at the physics of plasmas that are potentially good enough for power stations. Then in ITER, we've got here 2007, but of course that's a guess. We will be looking at that ignition process that we talked about, and we'll be looking at power station technologies rather closely. And then in round about 2025, we would build, or the world would build, a demonstration power station.
To achieve these ambitious goals, the involvement of industry is vital. European expertise in fields such as aerospace, transport and special materials has already spawned link-ups with JET, which are likely to bring long-term benefits in the next stages of fusion research. One such area is the development of carbon composites. The new heat-resistant tiles inside the torus are made of this material. The French company CEP uses its aerospace experience to fabricate the composite for the tile supports or carriers. A carbon or graphite with different thermal and mechanical properties is made by Dunlop for the tiles themselves. Machining graphite is a special art, and companies in the Netherlands and Britain fashion the slabs into tiles and tile carriers. Every surface is checked, as deviations might affect the stability of the plasma. Transport is a hallmark of the Italian engineering company Ansaldo. Some of the technology they developed for JET as part of their long-term interest in fusion research has been applied in this prototype bus, which is powered by fuel cells. On site at JET, it is the deployment of skilled manpower by the engineering company GEC Alstom which helps ensure the installation of all components to specification. Throughout much of 1996, the heating and fueling systems for JET were being refined and all the detectors being prepared for what was to be the climax of over a decade of JET experiments. For the first time, the likely fuel for a future power station would be used in a major experiment, the two isotopes of hydrogen, deuterium and tritium. The clue to a successful fusion experiment lies in the behaviour of a plasma at an atomic level. In a plasma, the individual particles are propelled around by their energy or temperature and the electric forces which exist between all charged particles. Usually, when two ions collide, they bounce off like billiard balls. But if the energy is high enough, they may interact or fuse. New particles are produced, and energy. It is the emission of the small particles called neutrons which generally provide the measure of successful fusion. The detectors to pick up the neutrons form part of the intricate three-dimensional jigsaw that makes up the JET experiment. But there is another challenge. The other product of the fusion reactions is hot helium ions. These are important because they sustain the plasma at an operating temperature by passing on their energy in collisions. However, when the helium ions cool down, they must be removed because they start to inhibit the fusion process. Removing the exhaust is one of the major challenges in sustaining the plasma. To achieve this, a device called a diverter is being installed at the base of the torus to trap the exhaust particles. Different designs are being tried out to see which proves the most efficient in sustaining the fusion process.
Move the boom to 17 OW, first rest point. Right.
Once tritium is used as a fuel, the inside of the torus becomes too radioactive for people to work in comfortably. So a remote handling operation has been devised to implement changes to the diverter and cope with all the maintenance and upgrading activities in a fusion experiment. The centrepiece is a boom designed to reach all parts of the torus interior with its own cameras and lights. Attached to it is what's called a mascot with arms to carry out the detailed manipulations. There is also a virtual reality computer system designed to help the operator. This is state-of-the-art technology, a unique mix of computerized and human control pioneered by jet engineers. To simulate conditions inside the torus, an exact replica has been built with similar lighting and access. Tests here could avert costly errors in the real operation.
It has actually been very, very useful from a test point of view. And in fact,
While the remote handling system was being proven to install the new diverter, the teams of physicists were honing their detectors to pick up just the signals required. In the roof above the torus, the laser system was nearing completion, ready to probe the plasma temperature and position. By mid-1996, the trial of JET's new design was underway.
All ready? Beams ready?
Each plasma lasts for less than a minute. The leaders of each session must adjust the magnetic fields and the injection of new plasma in the search for improvement. It's a trip into the unknown.
So now we're in the last 30 seconds of countdown. Gosh, that's quite a pulse, isn't it?
The results of every run are analysed and stored. Each team looks for clues in its own apparatus as to how the plasma is behaving with the new diverter.
Which is the bigger anyway? The 1 to 10 is larger, horizontal. That's the way around it was.
I think the laser energy is down a bit, and I don't know whether that. Do you think that's straight line?
Yeah.
In the middle?
Yeah.
In our old familiar 3 meter
Yeah.
straight line.
Yeah. We can see them.
As the world's fusion scientists meet, the spotlight falls on the JET experiment. Plans for the world machine will be influenced by news of developments from JET. As the researchers ponder the latest results, a key question lies in the background. Why fusion is so important is that it can offer future generations an energy option which they may well need with all the uncertainties surrounding present fuels. If the world waits for a major crisis in conventional sources of energy, the time to call on fusion energy may be too late. It is a subject which brings continents together in cooperation and competition.
The question is what happens in these 100 microseconds.
Which concerns nitrogen-related diverters that were quite frequently established at JET.
We see this deposit, which is 50% of deuterium in carbon, but I mean, what you don't know is actually in the machine at the end of the pulse.
A reminder of the tiny quantities of fuel needed for fusion power came as samples were unloaded in preparation for the big run. This canister contains just a few grams of tritium. In a real power station, just 1 gram of deuterium and tritium as fuel would replace 10 million grams of coal or oil. Also, the daily waste from such a 1,000 megawatt plant would be just 2 kilograms of helium for a fusion plant, compared to some 30 million kilograms of carbon dioxide, sulfur dioxide and other wastes from a fossil fuel plant. However, managing the fuel for a fusion plant requires special skills. A new facility has been built at JET to purify and recycle the fuel. This plant ensures that one of the hydrogen isotopes, tritium, is both recycled and kept isolated because it is radioactive. Safety is one of the foremost concerns in all developments towards fusion power, as it must be for any form of energy provision.
How safe is JET?
JET is very safe. It is not like a fission reactor. The amount of fuel in a fusion system is very small at any moment and consequently could only burn for less than a minute. The power in a fusion plasma is self-limiting and there is no chance of an uncontrolled runaway.
So there is no possibility of a Chernobyl-type disaster. Nurturing the vision of a clean, safe and efficient fusion power station requires bringing together both scientific and political skills in today's world.
Since I'm particularly interested in the diverter work...
The director of JET leads the scientific effort, but must also work directly with the European political infrastructure that underpins the project. In many ways, JET can be seen as a symbol of how the new Europe is working. The Commission in Brussels steers a fusion effort which includes the research in member states and JET, which spearheads the programme. The Council of Ministers and the European Parliament see that the political aims of Europe's energy strategy are met and approve the funds. It's Europe working at several levels: science and engineering, industry, European institutions and politics. And JET's latest experiment with tritium and deuterium as fuel has once more put Europe at centre stage. As the power is increased, JET scientists and engineers wait for the signs that the plasma is producing a new record in controlled fusion energy. This is the first time a pulse of more than 12 megawatts of fusion power has been achieved in a controlled fusion experiment. While a host of riddles still remain in scaling up the fusion process, this represents an important proof of some of the key technologies needed on the path to practical fusion energy. It is a reflection of the success of this European collaboration that a strong position has now been achieved by Europe as it prepares for the proposed world project called ITER. However history comes to place the JET experiment, one thing is sure: without such steps into the unknown, humanity may never have a chance to benefit from a potentially limitless fuel, a fuel perhaps cast to the needs of a new millennium.